On the last part of chapter 4, I would like to discuss the simplified method to eliminate those columns that having zero displacement since the beginning when we define the stiffness metric for each element. For that reason, let's have a look on the second example of a plane truss problem. For example, in this case, we have 4 truss members has been loaded at point B 20 kN at the direction shown and 10 kN at point D. All the dimension is given in the figure, as well as the material properties is 70 gigapascal and the cross-sectional area for the whole truss member is 300 millimeter square. Similarly to the first example, the first step we have to sketch the final element model of the whole structure, labeling all nodes and elements, and define the status of body conditions, or we call it degree of freedom, and the relevant loads and reactions. So in this case, we go at point by point. At point A or not A, it has been pin supported, meaning that it cannot move in X and Y direction. So that's why UA and VA is equal to 0. So once it has been supported or prevent from moving, so meaning that at node A, we're going to have reactions, force in X and Y directions. At node B or point B, we can see clearly point B is a free point or a free node. It do not have any support and it only has been load with a point load. Okay, meaning that point B can move in X and Y direction. That is why UB and VB is unknowns. And we can define the loads acting at node B by resolving this load in X and Y direction. We have the angle, so we can use 20 kN sine 30 degree for Y directions, and for the X direction we just need to cos 30 degree, so that we have the horizontal load and vertical load at point B. At point C, similarly to point A, it has been pin supported, meaning that UC and VC equal to 0, and as it has been supported by pin joint, meaning that it has been prevented from moving in X and Y direction, and it has the reaction forces in X and Y direction. And the last node, point D, it has a pin roller supported that show that this node D can move in Y direction, or able to move or able to have displacement in Y directions, as it can slide in Y direction, while in X direction it can't move. It's been prevented from moving in X direction. Therefore, UD is equal to 0 and VD is unknown. And please take note, at node D, we also have an applied load equal to 10 kN downward. So in X direction, we have reaction force FRF dx. At Y direction, we have load equal to negative 10 kN. So we can define from this sketching, the degree of freedom in this case is 3, which is UB, VB and VD. Similarly, the second step we have to do is to determine the stiffness metric for each element by using the K metric for a truss member. And please take note that in this example, the element has not been defined or provided to us. As I mentioned in the first example, always numbering your elements according to the sequence of A, B, C or 1 to 3. For example, in this case, we can define element 1 for member AB, element 2 for member BC, element 3 for member CD, and element 4 for member BD. I just follow the sequence of ABC. So once we have this information regarding the elements, next we just need to draw a table to list down all the important parameters in order to determine the K matrix. Okay, so remember, first column is for the element, second column we define for the element connectivity or nodes, how we connect the nodes. For example, element 1, we have to decide either we connect it from A to B or B to A. Remember, I always encourage you to connect the elements by follow the sequence. So for example, element 1, I connect it by using or from node A to node B. Element 2 is from B to C, element 3 from C to D, and element 4 from node B to node D. Next, what we have to do is to define the theta. For example, element AB is 0 degree, element 2 is 270 degree, as element 2 is from B to C, so the theta is from 0 until it reaches to that particular member of that particular element. So theta here is 270 degree. Element 3 from C to D, so meaning that is here 0 degree. Element 4 is B to D, so meaning that from B here to D, to this line. So that will be your angle. So you know this angle, okay, the angle is 270. So you just need to define this theta. Okay, we know this is 3. The length here is 4. So we can define this theta here by using tan theta. So that we obtain the theta is 306.87. The next value is to define all those values inside this matrix. Okay, for each element. And next, to determine the value AE over L or the K, we have to define the L. As we know the E, we know the A, but we don't have the information about the L, the length of the element. So if you define the length of element for each element, so we obtain these values, and then we can determine the K value AE over L for each element. Once we have defined this table with all the important parameters, next we can determine the stiffness metric for each element by using the stiffness metric equation. So in this case, here is the step where we can simplify our calculations by eliminating those columns that having zero displacement. For that reason, we have to recall back our boundary condition from the first step. For example, here I list down all the boundary condition for nodes that having zero displacement. So when we want to obtain the stiffness metric for each element, we have to check to this boundary condition. For example, in element 1 is between node A and B. So refer back to this boundary condition. We see here we have UA and VA. So we know this value are 0. So in stiffness metric of element 1, we can eliminate those columns UA and VA. So we always start, as we decide the element connectivity is A to B, remember, so we start UA, VA, UB and VB. As UA and VA is 0, then we can eliminate those columns. But we still keep the row. We do not eliminate the row because we still need the row in order to use it to determine the reaction force. That's why we keep the row. Unless if you have no interest to determine the reaction force, then you also can eliminate the rho. But in this example, I would like to determine the reaction force later on. That's why I still keep the rho that having zero displacement. And then to determine the value inside here, we just need to refer, for example, for this element 1 on the third column here and the fourth column in this matrix. All this value we have defined from here is 7. Just multiply with C2 here is 1 and the rest value is 0. That's why we obtain here negative 7 and 7. And then we do the same for the second element. We check in second element is between B and C. So we check here C is 0. Okay, UC and VC is 0. That's why we eliminate these two columns, UC and VC. And the rest value, we just need to refer to this table. Okay, for example, for element 2, we only has value for S square. The rest value is 0. That's why we only has these two value for K2. Okay, between column 1 and column 2. So you just need to refer column 1 and column 2. And we continue with the third matrix for the third element. In this case, the element, the node involved is C and D. So we check here, we have UC, VC and UD, meaning that 3 columns can be eliminated in this case. So we can eliminate UC, VC and UD in this case. And unfortunately in this case, the column for the last column, okay, for the third element, all the values are 0 because it's depending on CS and C square. So when we check in the third column, C square is 0, CS also 0. That's why you obtain all the value is 0. And the last element, element 4, is between B and D. So we check, we only has one column that having 0 displacement, which is UD. So that's why we eliminate UD here because its value is 0. And the rest value here, we just need to refer to the table here and refer to the K matrix equation here. And next, we just need to assemble all these matrices to form the global stiffness metric. And as K3 or element 3 having all 0 value, so we can eliminate straight away this third matrix from bringing to assemble in the global matrix. As I mentioned, the next step is to assemble all these stiffness metric to form the global stiffness metric. And now we only has 3 metrics as we eliminate K3 as all the value are 0. So to assemble or to insert the K matrix, we have to do element by element. Let's start with element 1. Before that, we can eliminate those columns that are 0 straight away in this global stiffness metric. For example, we know that UA, VA, UC, VC and UD is equal to 0. So we can eliminate those values in the global stiffness metric straight away. So next, you just need to insert the K1 value into this global stiffness metric. So in this K1, we only having UB and UA. So UB and UA negative 7 and UB. So UB we have 7 value here. Next, we need to insert the K2 value. Next, we want to insert the K2 matrix into the global stiffness matrix, which is represented by the blue color. Similarly, in this K2 matrix, we only has value for VB. So we check VB, we have 5.25 and VC. So VB, VC. So VB, VC. So we have here negative 5.25. The rest value are zeros. The next, we would like to insert the third matrix, which is represented by the green color. Started with UB and UB, so we check UB and UB. So we have here UB and UB overlap with the first K matrix, so we just need to plus, and then followed by UB negative UB VB negative 2.016 to UB VB. So here this value, and the third one UB UD. So UB UD, here we have this value, and the last one UB VD. So UB VD, we have this value. So just replace at the right position. That's why you have to put this reference on the top and also on the right of the matrix for your reference, in order to insert the value without put the value at the wrong place, at the wrong position. Next, we just need to sum up so that we can obtain the global stiffness metric for the whole structure. Please note that when we eliminate those columns, okay, so in this case, this metric is called the reduced global stiffness matrix. Okay, the term to call for this type of metric is the reduced global stiffness matrix. So next, you just need to apply the boundary condition to eliminate the row that not useful for the displacement calculations. So we apply against the boundary conditions so that we can eliminate those rows that not useful for the displacement calculations. So for example, UA equal to 0, VA equal to 0, UC, VC and UD equal to 0, so that we only has these three value in column first and three value in the row. So we're going to have a 3 times 3 matrix. Okay, so a 3 times 3 matrix. So in order to solve for the displacement, we have to set up the system linear equation, which is F equal to KU. So we have the K value. Okay, we have the K value, we have defined this. Next, we just need to define the loads from the steps one that we have defined. So by check for UB, so check UB. So UB we have 17.32 kilonewtons. Okay, and then for VB, so VB we have negative 10 kilonewton, and for VD, okay, VD we have negative 10 kilonewtons. So once we have all this value, next step we can solve the unknown degree of freedom, and we obtain the unknown displacement in this truss structure. The next step, if we would like to determine the reaction forces, as we know that in this structure, some of points have been supported by pin, so it will have the reaction force. Okay, to calculate the reaction force, what we need to have is the sketching of our first step as well as the displacement value. So by referring to global stiffness matrix, so that we can define the reaction force equation. For example, UA is for RFAX, VA is for RFAY. So to obtain the equation for RFAX, okay, so just refer to this one. We have negative 7 times UB, and don't forget this value, 10 power of 6, so that's why we have this value. And for RFAY, we have all 0, So that's why the value is 0. Similarly for FCX, RFCX, all those values are 0. Okay. And RFCY, we have negative 5.25 times VB. And for the last reaction force is negative 1.512 times UB plus 2.016 times VB minus negative 2.016 times VD. So that's why we obtain all these equations. Reaction force only occur on the row that having zero displacement. Okay, those rows that having displacement, we do not have any reactions. Please take note that. Another parameter that we can determine from the displacement is the element stress. As we define in part 1, stress is given by this equation. In order to solve this equation, we have to refer back to our table as we need to know the value of C and S that we have defined before, as well as the value of the displacement that we have obtained previously. For example, in element 1 is between node A, B. So what we need to know is the E is constant for the whole members. Okay, member element 1, the L will be the element for member AB, element 1. And then for this value, we just need to refer back to this table. So SC is equal to 1, S equal to 0. And we know that UA is 0, VA is 0. We only has value UB and VB. By replacing all those values, so we have this arrangement and we can solve this equation to obtain the stress is equal to 82.83 megapascal. Let's see another example. Let's say we want to calculate the stress for element 4, for example, is between member BD. Okay, member BD. So the equation will be E divided by LBD, the length of member BD. And the CS here, we just need to refer back to this value. And this value, we can refer back to our displacement that we have obtained. So by replacing all those values in these equations, then we can solve the stress for BD, which is equal to 41.75 megapascal. How to multiply this one? So negative 0.6 times 3.55 plus 0.8 times negative 3.81 plus 0.6 times 0 plus negative 0.8 times negative 10.2, 10 power negative 3. Once we have that value, then just multiply with this value to obtain this value. That's all for chapter 4, plane trusses.